It's
I do
not
have
too
a
much
question.
trouble.
Okay. All right.
I do have a
So
question though.
yeah. So
If that's the way you
okay.
want to start.
Before I open it up, yeah, let's see. Craig, you got any specific questions that came up as you were walking through stuff?
Uh, Not exactly. I just got to make sure I kind of get all the VMPs, IOCs, that kind of stuff straight, and which particular one to use in calculating outputs and inputs of the various PV system items and stuff. So it's just that's a practice thing for me. I think, you know.
Yeah, when we talk about let me go ahead and do the whiteboard here. I think I can do the screen share and then choose the whiteboard. Does that show up as the whiteboard there on your screen?
It does.
All
Yep.
right. So what you're raising there is it that's quite lovely. If I do the IV curve, I'm kind of cattywampus here, but the typical IV curve is going to look something like that. And the IMP is the theoretical maximum amperage that a specific panel, and this is the IV curve. And this IV curve only currently represents STC conditions. There's an infinite number of IV curves based on all the different conditions that might be in existence. But we usually, at least for rating panels, only look at STC. And STC, of course, is 25 degrees Celsius, 1.5 atmospheres, and 1,000 watts per square meter radians. So down here is going to be your VOC. This is going to be 0. And this is amps. And this is volts, which is why it's the IV curve. All right, so under these two situations, the theoretical maximum amps, the theoretical maximum volts, the panel will be generating 0 watts, right? Because anything times 0 is 0. Mm-hmm. So these are conditions you don't want to have in existence for your solar array. But these two conditions are only used when we're designing the system because they're the theoretical worst case scenario. So when we size the wire, we deal, I said IMP, it's ISC. So I've already confused
you.
Yeah, ISC. So we use ISC for calculating wire size so that we protected our system by using the worst case amperage condition. We use VOC when we're calculating the amperage, the maximum theoretical amperage for our system so that we stay under the National Electrical Code limits. Those are artificial limits. So, but for residential, it's 600 volts. So we're going to use VOC, but these are not real world conditions. So they're just design conditions. So when we're designing our wire system, we use ISC. When we're designing the string to see what our maximum voltage is, we use VOC. But when we're worried about real world conditions, that's a good line. Jesus, I can't. This little cat. Idea. Yeah.
Okay.
So this is going to be IMP, and this is going to be VMP, and this is the maximum power point, or Pmax. All right, so this is where we're going to be operating at. Well, if I want to figure things like voltage drop, I want to know what's happening in the real world, I'm going to use the real world amperage and the real world voltage for that. So when I'm trying to get real numbers that are dealing with my production, oh, that was better. I'm going to use the IMP and the VMP for that.
Mm-hmm.
So I think that's the way I remember it anyway, is just design, use ISC and VOC. For real world worries, I use the other ones.
Okay.
So, and if you talk about the curve, which I didn't realize I lost, I wondered why my drawing was so clean. The thing that affects amperage mostly is irradiance. So this would be at 1,000 watts per square meter. If I was operating at 800 watts, this curve would look something more like that. It still affects voltage, but not as much. And the thing that affects voltage primarily is temperature. So when it's colder, this voltage would range further out this direction. And if it's hotter, it would shore up in that direction. So temperature affects both amps and volts, but mostly volts. Irradiance affects both amps and volts, but mostly amps.
Okay.
So that's kind of, yeah, good to know anyway. You know, it doesn't really affect our calculations that much, but it's just good to know.
That's great.
Let's see. I might be better off just using my mouse than this pen. It's so funny. I have this little whiteboard thing here sitting, and I was having trouble with my computer one time because things were happening. The cursor was going all over the place. Turned out the little pen was sitting on the whiteboard over off to the side, and it was causing all sorts of interference with my screen and all of that. Okay, so so that's one issue. What about some of the other calculations while I've got the whiteboard up there?
Well, on the wiring design lab, the very last question, I was doing great right to the end, and then the question right before that came up with that the panel has a 32 amp max output, or I'm sorry, the inverter had a 32 amp max output, and the calculations came up with 29 amps, and then but except that 32 times 1 1/4 is 40. So the answer was 40, and I got that. But then I got down to the next question, and it says, okay, what size breaker do you use in the panel for that inverter to go into? And I said it should be 50 amps because I had a 40 amp load. So I said, well, I'm not going to use a 40 amp breaker on that. I'm going to put a 50 on it. And
No,
then, but it came down, but it used the actual calculation, the 7,000 divided by 240 times 1 is 36.46 amps. And so you could use a 40 amp breaker. So I was
the
okay,
reason
why,
is,
you know.
Yeah, your wire size, the output from the array or from the inverter in this case is like 32 amps, right?
Yeah.
So you're sizing the wire based on 40 amps, but you also size the breaker based on 32 amps, not 40. Because you know it still has the same, it's got to be at least what the rating of the wire is. But it's still 125% of what the actual throughput amperage is going to be. You know, the amount of amps going through the wire didn't go up.
Not the max?
No, the max, well, it's got to be that or less, you know, like you could have, I'm going to stop the share here. You could have sized the wire for 50 amps, right? Or 60 or 70 or 80, whatever, you know, it doesn't hurt to have bigger wire.
Okay.
But the breaker still would have been sized at 1.25 times the amperage that's flowing through that circuit, which was 32 amps. Doesn't matter what the wire size is in front of it, as long as the breaker is at least what the wire is. You don't want to put a 40 amp breaker on 30 amp wire because that's the same as having no breaker at all. Because the wire is going to burst into flames before the breaker trips.
It gets that, yeah, exactly.
I think I was looking at it backwards too, because I'm used to looking at a breaker with a load on it instead of being fed. So I was going, okay, well, I'm going to make the breaker bigger than my load. But
yeah, if you had
opposite direction.
If you had 40 amp wire with a 50 amp breaker, the breaker is doing you no good.
On burn out before. Yeah, it's going to burn out before because it's going to get higher than that 40 amp and then wind up burning that wire out.
Yeah.
Now, one of the things we run into occasionally is, I forget which wire it is. It's like 5 gauge or something, has not 5 gauge, but anyway, it has a rating of 55 amps. And so we've run into some problems where you say the wire's got to be 55 amps. If let's say that the throughput is 45 or 43 amps is what's coming through the wire. So you do all the calculations and say, okay, I got to put a 55 amp wire in there. But then you go to breakers, and the breakers only come in 50 and 60. And then you go, oh, geez. Well, I can't put a 60 in there because 55 amp for the wire, it's doing me no good. But if I put a 50 in there, well, that's not 120% of whatever the throughput is. And so you can run into that problem. The thing I do is just put a 50 in there, because the only problem you're going to have is nuisance tripping. If you get that, but you've already built in the fudge factor, and it's probably never ever going to happen.
Get that.
But the problem is you may have an inspector who's being real anal about it, and he may come back and go, you know what, that's not 120% of the throughput. And you're like, you're right. But and if he's still, then he'll go, well, then switch out the wire and put bigger wire in, and run it with a 60. And you're like, okay. So that's something to deal with. If you're really faced with that in the real world, you might want to call up the inspector and ask them before you go to that. But if it's only, the difference between the panel and the inverter is sometimes only a few feet,
right?
You may as well put in the bigger wire, because the costs are negligible. But sometimes putting in that bigger wire can be a pain in the butt, because now you're trying to do the twists and the turns and make the connections. And,
it's really thick.
And then of course you also run into, with the breakers, the holes in the breakers are based on the ampacity anticipated for the wire. So let's say you could put in 2-aught wire, and then you're trying to put in a 20 amp breaker to that 2-aught wire. It ain't gonna work. So at that point, now you got to get a bigger breaker, or what I've seen people do is they always call it a haircut, is you take the wire itself and cut off some of those strands, and then it's the same as having smaller wire,
Why buy the wire?
But of course, then if you're going to upgrade to a bigger system later, the wire's in place, and you can just snip off that little connection and not haircut the wire and put a bigger breaker in. And I think they do make breakers that have bigger holes with lower ampacity, but you got to special order them. And breakers are getting so expensive now. I couldn't believe I spent like $80 on a 100 amp circuit breaker. You're like, really? Why is it that expensive? So, all right. Okay. So that one, hopefully that makes sense, is let me just sort of walk through. I'll do the screen share again, and hopefully I'll have the whiteboard working properly it's my hand-eye coordination, not the whiteboard's fault. All right. So
another question before you launch into.
Sure.
On the microinverter system.
Yeah.
I was a little unclear because I can't see under my panels on my roof. How do they pull the wires together? Do they do them in series down the array and connect them together one to the other, or how do they?
Yeah, they've got. I'm assuming you've got N phase, but it's the same with all of these microinverters. The wire that connects the microinverters together is a proprietary wire, and it has a parallel connection port that the little connector on the microinverter connects into that parallel port. So it's making a parallel connection. So the line 1, line 2 are connecting to line 1, line 2.
So it's like a giant combiner box all stuck together down the road.
Yeah. Every single connection is like a combiner box. It's making a parallel, not serial connection.
Well, that explains a lot. I was so confused because I got it from that point down, but I didn't know how they were getting array put together, because I know there's only one wire coming down from my attic down into my basement, you know?
Yeah. Well,
Or
what ends up
two wires,
happening, what
three.
ends up happening when you're making those connections from each panel to panel to panel
Mhm.
is, because it's a parallel connection, the amps increase every connection. The volts stay the same.
Mhm.
With a series connection, the volts increase, the amps remain the same.
Yeah,
So that's why you've got a limitation as to the number of microinverters you can hook up in a branch circuit,
right.
because the size of the wire that they provided to you in that proprietary cable is 12 gauge wire. So
Mhm.
you can just look and say, all right, well then what did they do? They took the amp output of each microinverter, multiplied it times 1.25, and divided that into the capacity of a 12 gauge wire. And that's the maximum number of microinverters you can hook up in a branch circuit.
Yeah, I figured that out.
Yeah, so that's pretty straightforward. Now, if you have more than that, as far as the number of panels, then you take it to a combiner box,
Uh-huh.
and at that point, you connect them together.
That's, you just explained the whole thing. I couldn't figure out why my combiner box can be downstairs next to my panel.
Yeah.
You know, it's like, now I get it.
Yeah, and it used to be that you might have said, okay, let's combine them up there on the roof and then just run one bigger wire all the way down to the downstairs next to your panel. The problem with that, though, is that the N-phase system monitors and controls everything based on the branch circuit, individual monitoring of each panel. So then you've got to use a junction box, not a combiner box, and then you just run your 2 branch circuits or 3 branch circuits all the way down and connect them in that proprietary combiner box that
Okay.
N-phase has.
Well,
And
I
the
get away with that
N-phase,
because I only have 12 panels, so I don't
Yeah.
see any of that.
Yeah, but if you wanted to add, let's say you wanted to add another 12,
Yeah.
you could do that with your system, and you would just simply run another wire through that conduit, and
Yeah.
it would connect into another circuit breaker in that combiner box.
Right.
And that combiner box has enough capacity for 4 circuits.
Right.
And I think with the
Get
each
that
of
now.
those circuits is 20 amps.
Uh-huh.
So you can run up to 80 amps into that combiner box.
Spinning my panel can do that.
Yeah, so let's say that we're talking about microinverter systems here. So these are all microinverters, and they would come in, let's say I've got 3 branch circuits. I would end up coming into a junction box.
Mm-hmm.
And let's say we've maxed them out. So each of these is going to be running 16 amps because it's 20 amp maximum. So 16 amps times 1.25 gets you your 20.
Mm-hmm.
And then I would not combine them here, but I would come out of here with 3 different circuits.
Okay.
And these things would run all the way into your basement.
Yeah.
And then you got that big old N-phase combiner box.
Yeah.
And you've got the communication gateway that's up here in this corner.
Uh-huh.
And then you've got like a circuit breaker here that this one's going to connect into, and a circuit breaker over here that one's going to connect into, and one down here. And then you've got a spot that's empty.
Got it.
And then that's going to run from there. The combined output is going to go into an AC disconnect that's outside.
Yeah, it does.
And then from there, it's going to go and connect into your service panel right there. And then this is going to be your main, and that's going to be your meter.
So at that point, that would exceed the size of one breaker in my panel?
Well, if that's the case, let's say you're running 3 of them and each one's maxing out 60 amps.
Yeah.
Yeah, then you would probably, assuming you've got a 200 amp service panel here.
Yeah.
With 200 amp service from the utility.
Uh-huh.
It would exceed it. But if I had a 200 amp panel with 100 amp service from the utility, I could come in here with 60 amps and I'd be just fine. Because I'm at 160 on a 200 amp rated bus bar.
Mhm.
Normally, you wouldn't have a 200 amp service panel if you only had 100 amp service
Yeah.
from the utility.
Yeah.
But what you can do as a shortcut, let's say you decide I want to do a load side connection here, and I've got 200 amp panel and 200 amp service from my utility, and I can't put in 60. All I can do is put in 40.
Yeah.
40 is the max because of the 120% rule
Yeah.
for a service panel.
Mhm.
So what would I do? Well, one alternative would be to do a supply side connection, which would mean instead of connecting in here, I would have to connect in somewhere between the meter and the main.
Got it.
Well, to do that, you're going to have to hire an electrician to come out and disconnect yourself from the utility, and he's going to put a box or a splice in there somewhere.
An
And
AEP will be involved.
yeah, and he's going to make that connection. Well,
Mhm.
that can be a royal pain in the butt.
Ooh.
So another thing that you can do is swap out this main and go ahead and get yourself, let's say, 150 amp breaker. And even though you still have 200 amp service from the utility, I've capped it at 150 by swapping out the breaker, the main breaker.
Okay.
And now I could come in with 60 amps. I could come in with 80 amps and I'd still be all right. I could do my whole 80 amp if I wanted to, because 80 and a 150 is 230, which is still below the 120% rule for the service panel.
Huh.
So you could do it that way. The only danger there, you don't have to get an electrician, but bear in mind when you start disconnecting your main, that's something I'd like the power to be turned off before I do.
Yeah, no kidding.
So that meter box has to be removed.
Yeah, so you're probably still going to have to call AEP to have service interruption.
Right.
You know, to have that, because they don't want you messing with the meter. You know,
Right.
you could pull the clip and pull the meter and you'd be all right. But this is one reason why now in the real world, you know, they're starting to require that you've got the meter and then you've got a main disconnect panel out here.
Outside, yeah.
Yeah, so you could turn off service to your home
That'd be great.
and still be
Yeah.
okay.
Yeah,
Yeah,
other than
I
the
got a
neighbor
box
kid
like that.
coming over and shutting my power off.
Yeah, that's true. Or some neighbor kid or something like that. Yeah. That's always
But,
an issue. But
so-
it's
Is that something that you can, I just started reading about main lug load centers. I didn't know anything about that. I'm reading about that right now.
yeah.
So is that something you can add a panel to your panel?
Yeah. So if I've got a service panel here, and let's say this is my main, and that's going out to the meter, then typically you've got bus bars going like this.
Mhm.
And then oftentimes there's a connection point down here at the bottom of the bus bar. You could run wires to another service panel
Okay.
and connect in at the top of the bus bar here, and then, you know, have additional connections. So all of that is possible. Or you can also put a big breaker down here and run to this other service panel, or you could have another breaker down here like a main.
Okay.
But again, if you put another service panel in here, the 120% rule is still going to apply.
Okay.
So don't
Couldn't
think that I could put a 200 amp breaker in here, or 200 amp service panel, secondary one, and this one's 200 amp, and I've got 200 amps coming in from the utility, and then I say, okay, I want to now connect my system down here. Well,
Didn't matter.
at
It's only
this
limited
moment,
by that breaker
Doesn't
that
matter.
it's
I'm
connected
still
to,
same limit.
right?
yeah, well, I
Still
could put
limited.
I could put 100 amp breaker here, and you could think, okay, I've limited it, but I haven't really, because if I'm back feeding the full amount through that breaker, I've
Yeah.
exceeded it on this panel.
Yeah,
Okay.
right.
You
Alright.
know,
Yeah.
so, but this is usually used if you wanted to add a distribution network. Let's say you add on an addition, or you want to run it out to a garage or a barn or something like that, and it's all tied together. This is, you know, a lug panel or a main lug panel.
Okay.
Now, the other issue that you get into when you get into secondary panels is if you have your neutral bar and your ground bar in this service panel, in the main, wherever the main is located, these two are going to be bonded together. And that's either going to be with a jumper, or there's usually a green screw in one of them that connects to the box. But in every subsidiary panel, you do not want to connect your ground with your neutrals. You only want one place in your entire system where these things are interchanged. So oftentimes you'll see that they just randomly put ground wires and neutral wires, they co-mingle them onto these bus bars, and that's all fine in the main, but it's not fine in any sub panels.
Okay.
They have to be separated and isolated.
Okay.
Otherwise, you're going to get a ground loop. And the ground loop, it may not be dangerous, but it's going to cause interference. It's going to cause, your electronics, you're going to get weird buzzing. You're going to get some other issues. So, and the inspector will never approve it. So, that's just a given. So, and you can think about this in your house here, and that all makes sense. But where it's going to cause something tricky is, let's say you've got this main disconnect out here, and now you're coming in and connecting into a main here. And we're all going to still think that's our main, but it's not. This is the main. So now we have to keep everything separated here and not bond those things together, because they're bonded out here. So, and we have that at our house, where this unit is on a telephone pole that's 400 feet away from the house.
Wow.
So that unit then, and it actually has 4 breakers, and one breaker goes off to the barn, and one breaker goes off to the garage, and one goes to an outbuilding, and the other one, the pass-through one, goes to the house. Wow. And then this is where I connected my solar array, so it comes in here. And so this is the only place where the ground is supposed to be bonded to the neutral.
Very cool.
Although that said, I'm not 100% sure that because it's 450 feet away, that it makes any difference,
Yeah, right.
So anyway, that's the wonderful world of electricity. And of course, we live in a place that has no electrical inspection at all. So yeah, we're not even required to have electrical permits in our county. So
wow.
Yep. In fact, the only permitting that there's no structural permits, there's no electrical permits. We simply have, they come and inspect the plumbing. That's the only thing that they look for.
That's wild.
And the thing,
there's no safety issue.
Yeah, no. Well, you have fire hazards, electrocution.
They don't care about that.
They don't even care about that.
Well,
make sure that poop is getting to the sewage system.
Well, it's so funny too, because on our house, when the inspector came out, he was afraid to get out of the car because our big dog was barking at him. So he asked Annie, we have the Earthship, and he drew on a piece of paper a box like this, and all he said was, where does the septic tank stub out? Where is the stub out to the septic tank? So Annie just drew a little X like that on the front of the building. He goes, okay, all right, that's fine. And then he drove away.
Your anti-inspector device.
Yeah. But we do have a stub out right here for the septic tank, but we don't have any septic tank because we didn't want one. I mean, everything is composting, so.
Oh, wow.
But the code actually doesn't envision that you won't actually put in a septic tank. It says you must stub out to a septic tank, but it doesn't say you have to put one in.
You have to have one. Oh, wow.
So that was kind of, yeah. So we just simply capped off that pipe
Mhm.
and it's sitting there. So the house is ready if somebody wants to put in a septic tank, but we don't use it. So anyway, that's part of the wonderful world of inspectors.
Yes.
I know I had a student in class, Eduardo, who really good guy, and he took the class and then he got a job with a solar installer right away. And I mean, you guys know about the level that you'll feel confident with as soon as you're through this class. So he had installed like 3 residential systems. And then his boss said, well, you're going to be lead technician on this commercial installation. He's like, what? You know, it's
No
like,
problem.
yeah. So, and he's like 22 years old. So he's going, holy crap. So, so he called me up because it was a big system. It was a rooftop system. And it was like, I don't know, 800 panels or something like that. And he said that the inspector was going to come, and he knew that there was the requirement for a 4-foot walkway all around the perimeter on this flat roof.
Hmm.
He said, but the designer, when they factored in the panels, they didn't factor in the 1/2 inch for the bolts that go between the panels. So when he got to the end of the row, it wasn't 4 foot, it was like 3 foot or 2 foot, 8 inches or something like that, because of all of these 1/2 inches. So he was asking me, he goes, what do I do? Do I remove a row of panels, you know, for the walkway, or because there's nothing I can do? And I was like, hey man, that's not my call, you know, and you talk to your boss. And of course his boss is going, put in the panels, you know, and
Ignore it. He won't say anything.
yeah, so he's sweating bullets, Eduardo is, because the inspector's coming the next day. And he said the inspector got out in the parking lot and walked up and he goes, everything looked good up there? And he's like, oh yes, sir. And he goes, okay, where's the paperwork? And he signed off on the paperwork and then got in his car and drove away.
He said, I'm not climbing up there to see this.
Yeah, that's kind of what he
probably
said.
had a height thing going.
Yeah. And Eduardo, like, he called me up because, man, I dodged a bullet. And I said, no, you didn't dodge anything. You know, if there's a problem, you guys are liable. You know, it's like, not you specifically, but maybe your boss. So
same thing happened with mine. The inspector came because my panels go right to the edge of the roof.
Oh yeah.
The guy walked up, looked up, and he said, that's fine.
Yeah.
Didn't worry about the 3 foot 16-inch rules at all.
No.
They don't know about it, most of them, because it's not in the National Electrical Code. It's in the International Fire Code. And most of these guys study the NEC, but they have no idea about the fire code. And so they're oblivious to it. But if there's a fire, somebody's going to be aware. And oftentimes the firemen, if there's nowhere for them to stand, they're just going to go, you know what, just let it burn.
Step right on it.
No, they're just going to let your house burn.
They let it burn through. Okay.
Yeah, they won't put themselves at risk. You know, they'll just say, yeah, that's kind of too bad for you, isn't it? Yeah. So
hope the insurance covers it.
Yeah. So all right. So any other we sort of touched on that a little bit as far as the 120% rule. That's always something that gets people confused a little bit. You know, and that has to do with the bus bar rating of the panel, the service panel itself. And that's always a little confusing. Solar panel versus service panel. When we say service panel, it's basically your breaker box.
Those are inputs. It has nothing to do with the breakers you have that are outputs.
Yeah, the breakers you have are going to exceed usually quite a lot. Yeah, because the assumption there, and the reason they allow that for input is the only time that you're drawing, you know, you only draw from the utility what you're using in your house. So how many times have you ever popped the main breaker in your house because you turned on too much stuff? You know, so almost nobody uses 200 amps of power at any one time. So they're saying, okay, yeah, we realize that. So we'll give you a little bit of fudge factor in there. We'll say, okay, well, the 20% more, we'll give you 20% headroom on that. And because it's entirely possible your array is going to generate its full amount, so then you're saying, okay, well, then we'll just assume a lot of that is either servicing the load, so you're not pulling power from the array. And in fact, the only time you'd ever exceed that bus bar is if it was taking all the power the array was generating, plus another, 80% from, you could go to, let's say you have 40 amps coming in from your service panel and you're pulling 190 amps from your loads. You're only going to be drawing 150 amps from the utility. But let's say that goes up to 210 amps. Well, you're still now only going to be drawing 160, 170 amps from the utility. So you've exceeded the 200 amps, but that's one of the reasons they say put the breaker as far away from the main as possible, because the power is going to be feeding the loads closest to it
first.
And so your power is not doubling up and exceeding 200 amps. It's not running over top of each other. If you put it up next to the main breaker, then you may be feeding more than 200 amps down the bus bar, and you might burn out the bus bar. Because you're feeding from opposite ends. It's never going to double up and exceed that 200 amps.
Okay. So. And they put my EV charger down at the bottom of the box as well, but they left one open at the bottom. So if I could add another solar at the bottom.
I don't know. I would wonder, gosh. I mean, the closer the EV charger is to your solar array, I mean, the more likely it's going to be to use the solar power first. But I wonder, because it's such a big load, if it wouldn't make sense to locate it closer to the main. Probably doesn't make any difference, but I might. Usually you end up putting those things at the bottom because that's where the space is. It's like everything else above it is already filled up. Why should I move all that stuff? Let's just go with whatever's easiest. But all right. Any other questions? The main math questions that people worry about, and this is what I would practice, voltage drop equation. That's, hopefully you've gotten a lot of practice on that. Voltage drop equals amps times resistance times twice the distance divided by 1,000 feet. That's basically just Ohm's law adjusted for distance. Then there's the array sizing. The array sizing is going to be what do you do for sizing the array? You take your daily load, you divide that by the number of hours of irradiance you have each day. That gives you what the size of the array should be if under perfect 100% efficient conditions, but it's never 100% efficient. So you derate it, you divide by the derate, and you should end up with a little bit bigger array than where you started. Otherwise you did it backwards. That's how you size an array. So pretty straightforward. You take daily load, divide it by hours of insolation per day, and then derate it based on efficiency. With battery bank sizing, you take the daily load again. So the main things I found is if you know where to start, you can usually walk yourself through it. So for battery bank sizing, for array bank sizing, you always start with the daily load. And in this case, I'm trying to get, with array size, I'm trying to get from kilowatt hours per day to kilowatts. So what do I divide that by? Hours per day. Not 24 hours per day, but the hours of insolation per day. And then I have to worry about efficiency. With battery bank, you start with kilowatt hours per day. Well, I want to get to amp hours. So what do I divide that by? kilowatts or watts. So volts. Volts. Yeah, so how do I get from, so I divide that by the voltage of the system. So I take my kilowatt hours per day, divide it by volts, and I get amp hours per day. How many days of autonomy do I have? Well, now I'm getting to amp hours, getting rid of days. It could be half a day, it could be 2 days, could be 3 days, could be quarter of a day. It's whatever you've designed into it. And then I have to worry about efficiency. But it's not the efficiency of the entire system. It's only efficiency of everything from the battery bank to the load. Well, the only thing there is the inverter. So I divide that by the efficiency of the inverter. And then there's one other thing is depth of discharge. So depth of discharge, I can't use the whole battery. So how much of the battery am I using? So I divide by depth of discharge. That one's a little harder if you haven't done them 50 times, but it's kind of, that's the logic you're going through to get there. And then the one that seems to trip everybody up is the maximum and the minimum strings in calculating strings for a solar array with a string inverter. The nice thing about microinverters is calculation is pretty easy. How many inverters per string? Well, one inverter per string. Every string is one, that's it. Then you're worried about branch circuits, but strings, pretty simple. Also with power optimizer, pretty simple. How do I size the string for a power optimizer? I look at the spec sheet and it says for a P300, you can only do 18. There you go. Done for me. That's my only choice. It says minimum 8, maximum 25 or whatever it says. And that's what I've got to stay within.
Yeah.
But with a string inverter for the test, how do I start? Well, if everything was not dependent upon temperature, I would just simply say, what is the maximum input of my inverter? And what is the maximum output from my solar panel? And divide basically the input voltage of the inverter by the VOC of the solar panel. And that would tell me how many I could hook together in a string before the voltage increases above the capacity of the inverter.
Sure.
But that is, VOC is calculated at standard test conditions, which is 25 degrees Celsius. So, and I know that the colder it gets, the more the voltage will be. So now I have to say, well, what's the coldest day that ever existed at this particular location? You look that up on Google, you find out what it is in Celsius. You subtract, you find the delta between the coldest temperature and 25 degrees. So if it's minus 30, then you've got 55 degrees Celsius. Then the temperature coefficient says this is how much voltage it goes up for every degree Celsius. You multiply that times the number of degrees Celsius in difference, and it's going to give you a percentage. And now I take my VOC times 100% plus whatever the increased voltage percentage is. And that's now the theoretical maximum voltage that panel might produce on the coldest day ever. And then I divide that into the maximum input of the inverter. And that gets me my maximum in a string. And minimum is just the reverse with one other factor added in. And that's that it's hotter on a rooftop than it is the ambient air temperature. So when I talk about the difference between what is the hottest day ever and standard test conditions, I have to add in 25 degrees Celsius for a ground-mounted system, 30 degrees for a ballasted system, and 35 degrees for a flush-to-roof mounted system. And then I just do everything in reverse. I know that it's going to produce less voltage. How much voltage? Less? Well, it depends on the number of degrees. Then I take the standard test or the temperature coefficient, find out what's the minimum voltage that panel is ever going to produce. And then I have to hook up at least as many as is going to start up the inverter. So I look at my startup voltage, not my maximum voltage. And it used to be in the bad old days that many of these inverters had a maximum voltage of, let's say, 550 and a minimum voltage of 250. And when we did all of the calculations, it turned out we needed a minimum of 14 panels and a maximum of 12. And I'm going, well, this just isn't going to work. You know, I mean, it just doesn't work. So, so fortunately, they've reduced down the startup voltages. Usually they're in the 80 to the 90 volt range now. But that's one of the reasons they worked on that, is because sometimes you just had to spec out a different panel or a different inverter, because I couldn't do it in my location. Just, it wouldn't work.
Never work.
So those are the main math questions, I think, plus the 120% rule. You know, how do you calculate that? The other thing I wanted to bring up, let me just show you what I'm talking about on the whiteboard, is when we're sizing the wire size. Let's say we've got an array like this. Well, let's use the microinverter example, because this is something that's kind of real world. And so what I would do is, if I've got a rooftop here, and this is where my array is at the moment. And let's use yours, Gary, as an example. You've got 12 panels up there, and maybe it only fills up a small portion of your roof. Let's just
garage roof, but go ahead.
Yeah, let's assume it's only a little bit.
Okay.
But that's all that you needed at this point. Well, what I would do is I would design the system based on filling up the entire roof, as much space as is available. And then I would anticipate the wiring based on that. So let's say that if we're currently at 12 panels, but let's say if we maxed out the system, I could go to, let's say 39. Okay, so I could fit 39 panels up there. Well, I know with those microinverters, I can do a maximum of 13 in a string. So I would put a junction box in here where you're transitioning from your proprietary cable to whatever cable you're running the rest of the way. But I'd make sure it had 3 ports.
Okay.
You know, at least capacity, so I could add 2 more branch circuits in the future if I needed to. And then I would also put conduit in big enough, and maybe leave a pull string in there or something.
Yeah.
So that I could add 2 more branch circuits if I needed to, without a whole lot of problems. If
And
you're
only
really
one hole in the roof.
Pardon?
And only one hole in the roof.
Yeah, yeah. And if you're really feeling you're feeling your oats, you could even pull the wires right now and just leave them dangle. You know, you could max it out. You could just sort of cap them off inside that junction box, and you'd have 3 strings going down to your basement. That, I mean, wire's not going to get cheaper. So, you know, if you've got the money, especially if you're dealing with tax credits and maybe a REAP grant or something like that, where you're getting a lot of it subsidized, why not do it up front? Because later you may not have that tax.
Yeah, they go away.
So then you're going to come down here to the combiner box, the Enphase combiner box.
Yeah.
And the combiner box, you're going to come in, and you may not terminate these 2 wires. They may just be looped up somewhere, or you could terminate them into a breaker and just turn off the breaker if you wanted to do that.
Yeah.
And one of these breakers is going to be live. Well, each of these is maxed out at 20 amps, but there's spots for 4 of them. So 4 times 20 amps. Well, at that point, the output of this box could be 80 amps. So why not put in wire already big enough to handle 80 amps?
Absolutely.
Yeah, where you'd maximize that. And then when you come to this AC disconnect, well, normally those come in 30, 60, or 100 amp flavors for the AC disconnect. So why not go ahead and put in 100 amp? The difference between that and the 60 amp is probably $20.
Yeah.
Not a big deal. So go ahead and put in the 100 amp. If there's a breaker in here, well, you're only going to put a 20 amp breaker in there at the moment, because that's all you're operating at.
Yeah.
But you can swap out the breaker later.
Yeah.
And then the same thing from here to your service panel. Well, put in 80 amp wire.
Right.
If you're doing a load side connection, you're going to have to make sure you're aware that this system is probably not going to handle 80 amps unless you swap out the main with a lower breaker. But just pre-wire everything that you can to handle the maximum. So here we're saying, okay, the maximum output of the AC of this combiner box is 80 amps. So let's wire size everything to the maximum.
Mm-hmm.
In a string inverter, the system would be off of a solar panel or solar array, goes to a junction box, comes down here to the DC disconnect.
Mm-hmm.
From the DC disconnect, it's going to go into an inverter. Well, then from the inverter to the AC disconnect, we don't base anything on what came before. We base it on the maximum output amps.
Yeah.
Of the inverter.
Yeah.
And the reason for that is because we might add more panels or we might do more things up here, but let's just assume this is operating at a maximum.
Yeah.
So then everything from that point forward has to be based on that.
So would you end up, if you really expanded your number of panels, would you have a second inverter or?
You could for sure. And we've seen that happen a lot, where typically what's going to happen is, let's say that you've expanded your array and you would come in probably just with a duplicate system to this point and have a second one. And then you would probably have some sort of combiner here before you get to your AC disconnect.
Okay.
Because at this point, the outputs are all AC. So it's all going to be 240 volts. So you're just increasing your amperage. You don't have to worry about compatibility between the, like you have to with the DC and string sizes and all of that.
Then it's just you just be having monitoring of two different inverters, I suppose.
Yeah. Although more and more, you're going to have module level electronics up here on this. And so the monitoring is going to be individualized. And then just in your software, it's going to show up as array 1, array 2, and you can have them both in the same monitoring platform, assuming it's the same product.
Sure.
You could have an Enphase system here and a Solar Edge system here, have two different monitoring systems and do the same thing, combine the AC output.
Sure.
They don't have to be compatible at that point because the AC output is going to be compatible.
I hadn't thought of that. You're right. That's cool.
Yeah.
Yeah.
Another thing to consider, I don't know if I mentioned it before, but we've talked a bit about voltage drop. Voltage rise is another issue to think about when you're dealing with distances. And the concept of voltage rise is such, let's say I've got my array here. Let's use my place as an example, my farm. And let's say I've got the solar array and I've got microinverters up here.
Yeah.
And then they're going to my combiner box. And then it's going to an AC disconnect. And it's going to my service panel. All this is in my house, but this service panel ends up going out here to a telephone pole next to the road, and this is 450 feet there. All right, so I already have the issue of making sure that the power line coming in is adequately sized so that my voltage coming from the utility is actually something I can use in my house. In our situation, we ended up going with 2-aught wire, buried there, which was a royal pain to install.
Imagine digging a trench for that.
Well, it wasn't so much the trench, but it was pulling it through the conduit.
Oh.
We literally had 5 guys, and we had taken the mule and put the wire on a roll in the back of the mule, and because it was on a big reel, you
Yeah.
know, and it took a forklift basically to get it into the back of the mule.
Wow.
And then we were pulling it through the conduit. But the only way we could do it, even though we're using 2-inch conduit, I think, for the wire, is we laid the conduit next to the trench.
Mhm.
And that turned out to be a problem because we ended up pulling the wire all the way down the length. And then we had to take the conduit and feed it over each one section at a time from the end and run it all the way back the 450 feet. So we take a section and we feed it here and then walk it all the way down here to here, then take another section and walk it all the way down to here, and did that the whole way 10 foot at a time. And then once we had done 45 of these things, then
Wow.
we glued them all together.
Yeah.
And then dumped the whole thing down into the trench.
Wow.
Oh, that had to be like a ton of weight.
Yeah. Well, fortunately, Jimmy Braswell, who was helping, he's the electrician. He looks like Arnold Schwarzenegger. I mean, he's like a bodybuilder with the muscles and everything. And but there were 3 men and a boy, and I was the boy. So you know, it was definitely something.
Wow.
So anyway, okay, so the voltage rise. So let's assume, you know, what's the voltage here? Well, it turns out mine is I think it's right around 245 volts is what's being delivered at my meter. All right. So my inverter is seeking to output so that the voltage when it hits the meter is 245 volts. So if my voltage drop is, let's say I'm losing 7 volts over the course of this string, then my inverter has to generate at 252 volts
Yeah.
in order to get all the way here at 245. Well, what if the operating range of my inverter is 230 to 250? I've exceeded that operating range, and now my inverter is going to shut down.
Ain't gonna work, yeah.
And that's the result of voltage rise.
Okay.
Because the voltage has risen above the tolerance. And the way you deal with it is the same way you deal with voltage drop. You have to increase the size of the wire, decrease the distance, all of those kind of things. Well, sometimes that's not going to be an option. So we ran into this at an install I may have mentioned in Pennsylvania, where we installed like 18 microinverters and 4 of them were not operating. And when we did the troubleshooting with California, they said, oh, you know, you're in a situation where you're close to a power substation. So I think the voltage might have been around 250 volts, because when they generate the voltage at a substation, they set it high, because by the time it gets to the very end of the line, they've lost power too. And they've got to have at least 240 volts at that last site. So the closer you are to the substation, the higher your voltage is going to be. So that kicked up with voltage rise, the inverters outside of the tolerance of, it was like right on the border, and 4 of them it exceeded. So what they did is they were able to adjust the tolerance range within the inverter remotely from California.
Wow.
So they went in and just said, all right, we're going to go ahead and kick this up to 255 on your site. And now we're fine. And while I was talking to him on the phone, he goes, well, go out and look at the lights on your inverter. And I went out and I was like, yeah, they're green now. You know, he goes, okay, well, that's taken care of. So I was like, oh, okay, well, perfect. That's good. That's
Wow.
that's artificial, and I said, the Internet of Things, neither one of us was necessary. My inverter should have been smart enough to figure that out, and
Yeah.
Enphase should have been smart enough to make the adjustment.
Right, right. Mm.
All right, so I think those are the top things. We've gone over a little bit long
So
today.
if you, in your situation there, so your house is in phase, but you could have a barn that's, or a ground mount someplace that's, Solar Edge and
Yeah.
run it out to your pole as well.
Yeah, well, what I ended up doing, of course, for us is I actually ended up putting my solar array right here and made the connection down here, and it's only 90 feet.
Okay.
So that was an easy connection point.
Mhm.
So that's how that works.
Yeah.
But then we had the electricity, the wire that went all this way this summer, in fact, blew out somewhere, I think due to a lightning strike. So we had to replace the wire all the way to the house.
Wow.
And that was fortunately the insurance paid for it, but because it was like 12 grand just to replace that wire.
Wow.
So yep, it's
Can't
an
splice it.
expensive process.
Mhm.
All right. Okie dokie. Well, I think we're all set now for over this next week. You guys should be finishing up the book,
Yeah.
ideally. Finishing up all the exercises. I'd spend a little time on the math, and we can try next week to cover whatever is still you're unsure of. And then our date here is, let me make sure I bring up the proper date. I'm showing the 9th and 10th.
Mhm.
And you guys are all squared away. It's at 622 8th Street in Marietta, Ohio.
Mhm.
And you're all going to be staying at the Lafayette Hotel.
Yeah.
Are you going to be commuting,
Yes.
Gary, or are you going to stay?
Oh, I'm
Gary?
gonna stay.
Yeah.
I'll stay. That's too far. It's 2 hours or 2.5.
Yeah. No, it's a nice, and the hotel's a nice little,
Yeah,
don't
it is.
think you're going to be at the Hilton, but it's a funky
Oh, it's
old time,
nice.
old
I
school
like
thing.
it. I like it.
Yeah.
Yeah.
I think they may even be having some carriage rides around downtown Marietta in the evening as part of their like Christmas time. So you guys are going to be right there in the heart of that. So in the evening, if you want to go out on a little carriage ride and ride the horse-drawn carriage around downtown Marietta,
Yeah.
that I think my wife decided we're going to do that this year. So
Oh, awesome.
so I
Look
think
at
you'll
dinner.
enjoy it. Are your wives coming for this at all, or is it just going to be
Just
No,
me.
just
me.
batching it? Yep.
Yeah.
So, all
Mhm.
right. Well, you two can snuggle up together in the carriage.
We'll go to dinner.
Yeah.
Take a carriage ride to dinner.
Yeah. There's I will, we'll make some recommendations around, but there are some nice little restaurants around downtown. Certainly all walkable,
Sure.
to the Marietta, the Lafayette actually has a really good breakfast in their restaurant. I've never eaten dinner there, but there's some nice restaurants just within a 2 or 3 block walk. All of Marietta is a nice place to walk. I just encourage you to plan on that while you're here. It's got river trails, and the downtown is kind of functional and small, and there's a Marietta College is not too far away, so just walk around. It's nice.
I heard it had a snowstorm there though recently, hasn't it? Just got hit with the big snowstorm of some sort in Ohio. I'm not sure if it's that area, but I just heard Ohio.
Yeah,
Right,
we're
Cleveland.
kind of
Detroit.
we're way
Cleveland got
south.
hit.
Oh,
Cleveland
okay.
got hit. Well,
Yeah,
we've been
Cleveland got hit.
talking. It's been blowing a little bit of snow outside. I saw it here, but it's just little flurries. There's nothing going to
Okay.
stick to the ground. No, we're
Yeah.
kind of in the Florida of Ohio.
Oh, well, that's great.
Not only in weather-wise, but also I think in political temperament.
Yeah.
So
Yeah.
Excellent.
it's
Need
the
a
crazy.
passport.
The crazy man. Yeah, you need a, well, we're right across, I mean, you'll be looking out across to West Virginia from your hotel room.
Right.
And
Wow.
and West Virginia is what it went 42 points to Trump. I think
Mhm.
that's what it was in the last election.
Yeah.
So this is definitely
Cold country, cold
That
country.
Whole
includes the cities. It's not like Ohio where Columbus is Democrat.
no, Ohio is I love the description they gave of Pennsylvania, and Ohio is very much the same way. But James Carville during Clinton's campaign described Pennsylvania as Philadelphia and Pittsburgh with Alabama in the middle.
Yeah.
And that's
That's
basically
Ohio.
how
That's a good
Ohio
mix there.
Ohio's the same way. Yeah.
we're basically the three C's: Cleveland, Columbus, and Cincinnati, and then Alabama. You know,
Athens is a wild card too. though.
yeah, Athens is where OU is located. And also Oxford is a little bit where
Yeah.
Miami.
Yeah.
So you get a couple of little university, but Athens is a weird world because it's such a sparsely populated county with more than half the population are students. So so it's like this little island of blue in a sea of red. So
Oh my goodness. All right.
okie doke. Well, I'll talk to you guys next Tuesday.
All
And
right.
as I mentioned, I won't be doing the Solar Noon Tuesday, but we'll still have our session at 1 o'clock.
Okay.
All right.
Excellent. Have a
See
good
ya.
day.
Take care. Bye-bye.
Take